Hello, everyone. Welcome back. We are continuing our work on the first law of thermodynamics, but at this point, we've moved into chapter 8. And chapter 8 is going to work through some of the applications of the first law and trying to actually work to understanding engines and how we convert chemical energy into mechanical energy. So in this video, we're going to talk about isothermal expansions. You can find this in chapter 8.1. Okay, so let's make sure we know what an isothermal expansion is. Basically, we are going to start in our initial state with some pressure, volume, number of moles, and temperature. And we are going to expand the volume. And this volume is going to get larger. And we're going to expand this volume to some new pressure, new volume. But we are keeping the number of moles and the temperature the same. And the temperature staying the same is the key part of isothermal. This means that my change in temperature is equal to 0. So with all of this, we are ultimately going to try to figure out what work is for our system. And so we start, as always, with this definition of the first law of thermodynamics. So where we have that dE equals dQ plus W, which can also be written as TdS minus PDV. And I'm going to put this plus mu dN in parentheses. If the work is done reversibly, then we know that this dW is equal to negative PDV. And if we do this reversibly, we can get rid of these differentials by integrating both sides, and we find that work reversible is equal to the integral of negative PDV. Now, if the gas can be treated as an ideal gas, then we can get rid of this pressure because we can say that pressure is equal to nRT over V. And we can substitute that in for P, and we get that work reversible is equal to minus nRT times the integral of 1 over V dV. Now, if you don't happen to remember your integral rules, the integral of 1 over V is going to be the natural log of V. And then if I plug in V2 and V1, this is what I get. Because the natural log of V2 minus the natural log of V1 is equal to the natural log of V2 over V1. These are the log rules that we always have to relearn. And so we now have a very useful equation for when we have changing pressures, like we have here. And so since we have changing pressures, we now have an expression for work that doesn't involve pressure. So what does all of this mean? Well, in an isothermal expansion, work is being done by the system on the surroundings. And based on the equipartition theorem, we know the definition for the energy of the system. And so the change of energy is going to just be 3/2 in R delta T. But we're at isothermal conditions, and so this delta T is equal to 0 because the temperature isn't changing. And so that means that delta E is equal to 0. And so that means that because dW isn't 0, we know that Q cannot be 0. So what we have here is a system in which my temperature isn't changing, but heat is flowing. And so we need to remember that heat is the transport of energy, and temperature is more or less the storage of energy. And so in this case, work and heat are involved. So, in summary, in an isothermal expansion, the change in temperature is 0. The change of energy is 0. Work is going to be less than 0 because it is an expansion. And because delta E, I'm going to simplify, is equal to the change in heat plus the change in work. If the change in work is negative, that means that the change in heat has to be positive because we know that dE is 0. But the other thing that we know with this is that our entropy of the system is positive because the entropy is dQ over T. And since dQ is positive, that means that ds is also going to be positive. And so the energy in the system is flowing via both heat and work in an isothermal expansion. Okay, so in the next video, we're going to talk about adiabatic expansions, and I'm going to work to make a comparison between these two different types of expansion work.